Hello and welcome to this Intelligent Light webinar, Making Collaborative CFD Fly. My name is Shane Wagner. I'll be your host. And before we begin, I'd like to point your attention to the chat feature in the lower left corner of your ReadyTalk window. We'll be having a Q&A at the end of the session. And if there are any questions you have anytime during the webinar, you can use chat to ask the questions, and later I'll ask them on your behalf and our presenters will answer the questions. So thank you for coming. Let's begin. It's my pleasure to present our three presenters. Nathan Hariharan is the chairman of the AIAA Hover Prediction Workshop. Earl Duque is Manager of Applied Research here at Intelligent Light. And Michael Senesais is the Chief Technology Officer for R Systems. Today's agenda, we're going to be looking into the world of rotorcraft CFD. And this is really a challenging problem, and we're going to learn from Nathan what makes it so challenging and what the needs of the community are. Earl will then take us through some of the work that we did for the automated, standardized custom workflow that enabled us to, enabled the participants of the workshop to share and compare results. And Michael will talk about what R Systems did to provide a common HPC resource that made this all possible. And then we'll have the Q&A, as I mentioned. So at this point, we're very pleased to have Nathan Hariharan to describe what a challenging problem this is, and take it away, Nathan.
All right, thanks, Shane. Shane gave a rough outline. I will be talking primarily about the basic problem that we are trying to solve, which is the rotorcraft in hover. A bit on the background on the history of how this happened, and then hand it over to Earl on the workflow of how the 3D data viz and the data mining was achieved. Let me introduce my co-fellows, the working group members. Dr. Robert Naducci is a fellow of the Boeing Company, and Mr. Alan Egoff, who is with Sikorsky until recently retired, but is very active with the working group. And they have been a very active part of the group right from with the very inception, and part of all that's been achieved with the group. So let me dig in. Rotorcraft in hover, standardized simulations. So what is special about this problem? Why is hover important for rotorcrafts? Clearly, the difference between rotorcrafts versus fixed wing is the ability to hover. I can always argue that some aircraft with vector thrust can actually do it, but the primary distinguishing feature of a rotorcraft is this ability to hover. So you see two pictures in the slide. One on the top left, which is the US-60 Black Hawk in hover, and the second one is the B-22 Osprey. And you can see the condensation making it possible for a physical build of the trailing tip-vortex system. The hover condition represents the real value of the helicopter. And it's also at sort of a limiting design point in terms of what's the power required to carry the right amount of payload. And so the ability to predict that and predict it accurately is very helpful, and in not only the design but on analysis of existing rotorcrafts. The thing about rotorcrafts is that if you look at the two arrows pointing out to the condensation trails, the wings are largely dominated by these very strong tip vortex in the vortex system, which have a large influence on the performance of the rotorcraft. So the challenge is often to how well we can model that. So why is the first principle simulations for hover so challenging? What do I mean by first principles? These day and age, it's usually either Navier-Stokes or even sometimes LES. So the idea is to capture and predict the aerodynamic loads on the rotorcraft based on without any modeling of the vortex wake. So if you look at the right, there are two pictures. The one on the top, it's like a sketch from back in the 1950s when folks actually put a blade in a smoke tunnel and looked at the wake and sketched out what the wake looks like. And that consists of a very strong tip vortex and also the wake sheet and forms a classic helical pattern which sort of lurks underneath the rotor. The picture at the bottom is exactly the same sort of thing, but it's a simulation from a recent high fidelity tool and using visualization tools to look at the exact same thing. So that is the kind of inputs we are looking at to see, to dig into the wake. Classically, rotorcraft vortex systems are referred to as the wake up. The first principle simulations try to model this whole thing without any external inputs, either empirical or reduced order models. The trouble obviously is the numerical methods are very dissipative, and the biggest challenging task here is that if you imagine a rotor blade and typical CFD measures to the far field would require at least a 9-10 span-wise extend outside. If you look at the domain of how much you want to simulate versus the smallest feature you want to capture, which is the tip vortex, which is typically 1/10 of the chord, it becomes the range of scales that you need to model is large. And that means a lot of grid points, and you need to be very accurate. So it's very challenging. Also, there are some very unique problems to rotorcraft in hover because the entire system is set up by itself. There is no stabilizing mean effect. There is a lot of feedback between the vortex strength and the vortex system dynamics. So that makes it even more challenging. This is where back in 2011, as part of the AWS Applied ROTC, and proposed and initiated an effort to look into hover specifically. The groups wanted to bring together all the rotor heads across DoD, NASA, industry, academia, and other institutes around the world. First thing was to assess how well are we doing, and also what are the challenges, so what's remaining. Once again, if you look to the right, it's on the top is the same picture of the U60 in hovering mode. At the bottom is a 3-bladed tram simulation, and that's a complete Navier-Stokes simulation with the vortex being captured very accurately down to the farther extent as it persists. So the idea was to have a group that brings together the experts and they take all the tools out there, try to see how good are we doing. The focus and challenges when we formed the rotorcraft group, there was already an extensive effort on trying to model rotorcrafts in forward flight. It's a well-known US60 airloads workshop that's been going on for more than 10 years. And they've done substantial work in understanding the critical points of what a simulation needs to capture in forward flight. But there was no similar effort in hover, and that's where we focused our effort. There's several challenges. Typically when you talk about hover, what ends up happening is most of the realistic hover data, the dates almost 20 years back in terms of internal tests. Anything that is real and current is also very limited in distribution. Most companies like to keep the footage data to themselves. But if you want to run a workshop with a standardized evaluation, you need to have the geometry open. So we had very limited choices on what we could send out. As I'll show you later, the geometry of initial focus was the F76. But there's a recent excitement because NASA and Army are putting together testing for the PSP blade. The picture on the right shows a preliminary test at the Langley's rotorcraft cell test center for the PSP. And this test promises to take and give data on the wake, on the vortex strength, etc., which would be very useful to simulate further. So going forward, there's more to look forward to. A bit more on the first principles rotorcraft hover predictions. These people have been trying to do this for the last 20 years. Initially, it was just a challenge problem, and now these have become fairly routine. What has made it more practical is a combination of higher order methods that preserve these voting systems. OSET methods makes it easier to put the points where it is needed. Several codes have adopted the Cartesian framework, which is actually quite good in terms of having the construct higher order methods as well as how compact the data storage is. And finally, adaptive scalable measures, which is the more processing you can throw at it, it will scale well with one number of points. The picture on the right is a tram simulation of a tram in hover, or tram three-bladed rotor in hover. And you can see how well the tip voting system is picked up. This is a Helio simulation, almost more than 200 million points. The tremendous advancements in there, but nonetheless, the challenge of being able to, if I given a new rotor blade, can I very accurately predict the loading is still an open question, and that is where this workshop comes in. So, as I said, the need for rotor in hover prediction and the underlying physics of the wake are very tightly integrated. What often happens is when you have several codes, when you are looking to predict the performance of a rotor blade, the integrated loads often look similar, but the underlying physics basis is completely different. Trying to correlate how good the wake physics is captured to the ability to consistently predict the loads is of critical importance, and that's why we put together the idea of teaming up with LDK and Intelligent Light to see if we can standardize integrating the computer 3D fields. It's quite challenging because when you're talking about multiple groups, multiple solvers, there are different types of solvers, structured, unstructured, different types of grid systems, obviously periodic overset, data types are different, data sizes range a lot. Some simulations are more minimalist, some more billion cells. So taking this all together and trying to have a consistent set of integration for the physics is daunting, but that's what we embarked to do a couple of years back and sort of went out to the path. This is achieved through Intelligent Light, Earl's team, they're writing all the scripts, doing all the work with the our systems are hosting it, and they're going to talk about it more down the line. A quick history of the standardized sessions. We have been running this for the last 4 years. 2018 would be the 5th year. First year we started with the baseline S76 hover solutions, and in the second year we introduced tip shape variations. The S76 did have tip shape data, integrated data, so it was something to go by. In the third edition, we started with parametrics, including numerics, grid convergence, what's the turbulence models, and such like. And that's when somewhere in the aviation time frame, Earl and I were discussing on the sidelines, and that's how this idea came up in the first place. And that's where the first 3D standardized analysis took place. And we continued that in the fourth session. More numerics, more deeper integration into transition matter and things like that, more physics. And this was the session where we started introducing the PSP data also. So 47 papers, including the 27 at 17th session, and there's more on tap for 2018. This is the call for papers from last year. We have a similar call for papers for 2018 too. And the two different platforms, S76 and the NASA PSP, which these are the standardized platforms that we asked every participant to provide results in a 3D format, and that could be integrated. For rotor heads, this is the actual X76 configuration. I'm not going to go through all the details here, but it's a very realistic configuration. It's very similar to the US60, but with a linear twist. 17 participants. Largely, the rotograph community is not that big when compared to the fixed wing, so the players are usually the usual suspects that are very similar. These simulations do require a lot of compute time. So sometimes when you have a 4 or 5 year efforts running, there are years when one participant will drop out, but they come back. So you can see across, we have DoD represented, NAVAIR, AFDD, ADD right now, universities, Boeing. There's also Bell partnered with the University of Toledo, and it's a fairly representative of the rotorcraft industry, including healthy international participation. The key issue here is the focus on the physics, because often what ends up happening is you can get good results without getting the physics right. So the focus was to try and dig into the 3D data and try to get all the physics, like what happens to the wake under high stress conditions, things like if you have an elastic twist winder, what does that do to your wake? There's so many things you can look into, but not all of them have the same degree of effect on the ultimate loads. But the ability to predict a new rotor blade often hinges upon whether you get this right. And because of that, I showed the slide before, but this sort of leads up to what Earl is going to talk. The bottom line takeaway here is that integrated loads often can look similar, but how you do the underlying, captures underlying physics of the wake often determines how good the solution is consistently when you predict newer blades and different configurations of design conditions and such like. So capturing that is very important. And since this is an effort at capturing different solvers in different groups, a standardized way of integrating this data and trying to mine it is what this effort is all about. And I hand it over to Earl to talk about how it actually was done.
Thanks, Nathan. This is Earl Duque, Manager of Applied Research here at Intelligent Light. And several years ago, we were approached by the committee, and they said that they needed an easy way to compare their different types of CFD cases of the rotor that Nathan had shown. And this was complicated by lots of different types of meshes, different solvers, and people distributed around the world. And they needed to directly compare the wake structures, both visually and quantitatively. For the quantitative way, they needed a way to automatically derive the vortex paths, and they needed this all to be standardized in an automated post-processing workflow. We addressed these needs by developing a standardized post-processing scheme based upon FieldView. And with that, we utilize FieldView's FVX programming capability that in order to develop a automated tracker to determine the helicopter rotor tip vortex core. This was based upon the Q criterion, as shown here as an isosurface. And through that Q criterion field, we also took slices at different azimuth positions, and from that, we were able to determine the geometric centers for the tip vortex. These visualizations also allow qualitative comparisons. So those isosurfaces I shown previously in the coordinate cut planes of the Q criterion gives us qualitative comparisons also. And then we also were looking at different flow quantities such as the vertical velocity or W velocity shown here in the images on the right for 4 of the different cases that were submitted. All this was done within a FieldView XDB workflow that enabled sharing of FieldView XDB extracts amongst different collaborators that they could then use within FieldView or also within the free viewer XDB view. Now, within a typical post-processing workflow, the user would load the large CFD data sets into the post-processor, and then the post-processor would then create different objects, such as geometry, cutting planes, isosurfaces, as required by the domain expert. The domain expert would then operate on those objects to visualize the flow field, to create animations, to integrate surface pressures, for instance, to get forces, probe the flow field data, and then create images that they can then view and share and as part of their analysis. One of the big issues with this workflow is that the loading of the big CFD data and then computing the various objects can take time to both doing the reading and also memory in order to compute the objects. In a FieldView XDB workflow, we split this process here, where after the domain expert has created their objects, we write out an extract file, a FieldView XDB. The FieldView XDB can then be later read by FieldView or the FreeView or XDB view, where then the domain expert can then operate just on the surfaces to do their images and do their analysis. So FieldView XDB can be created from the user interface in FieldView, or you can also create these in batch using our FieldView scripting language or FVX. As mentioned, these surfaces or extracts can be read by FieldView or by the free viewer XDB view that you can download from our website. These surfaces are numerically identical to what's internal to FieldView, so that if you're integrating on the surface or from an extract or a surface that you created within FieldView, the integrations would match, for instance, on the surface. These surface extracts can store your choice of the quantities. They can be scalars or vectors. Different types of metadata can be stored inside these extracts. Oftentimes, we'll output just the quantities we need on that surface in order to perform the types of integrations and images that we need downstream. What's really interesting here, too, is that these surfaces are hundreds to 1,000 times smaller, which makes them much more easy to transfer and to share with your collaborators. For this project, we set up a collaborative workflow whereby users from around the world can upload their data sets to an anonymous FTP site located at our systems. The data sets they came across were Plot3D, or Overflow, so those are structured data sets. They were hybrid, so it could be a near-body structured grid with particles that are already pre-computed by the methodology. There's also unstructured data sets. The unstructured data sets can be in FVUNS format or different types of unstructured data formats that we support in FieldView. FieldView was then executed in batch on the R systems computers in order to create the various XDBs using our FieldView FVX program and also Python. FieldView 16 was also used interactively between our local systems and the R system computers. This allowed us to interactively explore using client-server mode some of the initial solutions that allow us to do initial setups for one type of grid system and then replicate that process on all the different types of grid types. Shown here is a close-up of 3 different submissions from the participants. On the left is a overset grid system that was computed on using the Overflow 2 code, and this is the solution that I provided. This is an adaptive overset grid. As you can see, there's some regions, little blocks, with more refinement. And on the middle is a submission from Boeing. And one thing to note is that the near body grids, the grids around the blade in the middle there, those are the same grids as the Boeing grid and the grids that I used. The main difference is that the off-body grid is cylindrical, and also it does not refine. It's just a fixed cylindrical grid that follows the flow. On the right is a submission from Cased. So you can see here the near body grid is an unstructured tetrahedral mesh overset onto structured Cartesian meshes. So these are examples of 3 types of grids that were submitted for this workshop. This image shows 11 different submissions, coordinate cut planes at x equals 0, colored by vertical velocity. So high velocity flowing downward is colored by the darker colors, and the lighter colors are flow going up. So one of the things we were looking at with these images is what's the difference in the breakup of the vortex structures emitted by and captured by the flow solvers. And one of the things we can see here is that there's a lot of difference between the different wake structures that are captured. Some of the wake structures are showing really fine vortex details, vortex structure details, and some are much more smooth. Shown here is another image showing the isosurfaces of Q criterion. And what you can see here, the cases labeled ILF, ILA, Army, and UTK, they all capture the tip vortex very tightly. And then as the tip vortex convects downstream, the vortex breaks up into really small, fine vortex structures. Whereas the other submissions from Boeing, Case, Onera, Maryland, and ATD, the wake structure, it forms a really tight vortex, convects downstream, and then diffuses out. We don't see the same behavior of fine vortex structures forming. But at the same time, these are all predicting very similar rotor thrust and torque behavior. So the results from this workshop, from the visualizations and XDB extracts that we created, were made available to the different participants. The XDBs, FieldView XDB extracts are available for others to view. They can use those within FieldView, or they can even download the free viewer from our website, XDBview, to look at these extracts. The post-process images that I just shown you, these are a few that we had created. We presented in a paper and also at the conference. And at the conference, that was at SciTech 16 and SciTech 17, we were able to share these with the participants during the conference and also at our booth, where people came to our booth and we uploaded and looked at the XDBs and interactively allowed people to interact with the data themselves, and that really helped all of us as a group to understand and get better understanding of what being predicted from these different methodologies. So this type of collaborative workflow is also something that can be customized for other domains. It's an opportunity for you to be able to we can customize these methods and these types of post-processing workflows to satisfy your own CFD post-processing needs. With that, I'd like to pass the baton off to Mike. So Michael, it's yours.
Thanks, Earl. Yeah, this is Michael Sinisize, Chief Technology Officer with R Systems NA Inc. We are a managed HPC services provider. We've been in business since 2005, giving access to bare metal resources in a variety of use cases. One of the primary drivers of our infrastructure are dedicated long-term contract models where we act as an extension of your in-house compute capacity and provide secure environments for your compute. And these can be highly scalable environments. And in another usage of our infrastructure are utility or shared usage clusters. Think of them kind of like shared academic resources, where you get to choose the best available node types for your configuration and pay per use for the jobs you run, with the R Systems HPC team providing expert white glove service to make sure you and your applications run efficiently. So our success story with working with the Hover Prediction Workshop with Intelligent Light and APAA is that if we provided a common HPC resource, data structures, queues, and software so that participants could selectively share data, videos, and project files on the same resource. So there wasn't a lot of spin up and spin down. The R Systems team helped with the integration of the user accounts, integration of softwares, and made it really easy to onboard new participants into the workflow and reduce any sort of IT friction you often find using external providers. So the path to success that Roger was looking for at Intelligent Life was to have high-performance clusters that can scale. The XDB workflow becomes easy to use when you have resources that can run them without slowdown. You get a lot of great performance per job. Large-scale jobs are possible, and you don't have to worry about provisioning storage or provisioning resources depending on your job size, as it's all there and available. Another value add that made this partnership so successful is that our IT team made sure that all the users that were onboarded for the various participants had the right information and sometimes hand-holding to get them integrated into the environment, get their data uploaded, and help them make sure they were using the right resources in the right way. Another the benefit to our business model is that versus other cloud providers or other resource providers, we do accounting based on the actual job usage instead of when the time an instance is up or when you're logging in and viewing your resource files or setting up jobs. The multi-user environment made it so that users didn't have to transfer data in and out of instances back into their enterprise and up into other users and participants' grids to do the XPD workflow modeling. And that sums up our system's participation in the Intelligent Light Hover Prediction Workshop. Back to you, Shane.
Well, thank you, Michael, and thanks to all the presenters. To sum up what we did here with the collaboration with the AIAA Hover Prediction Workshop, it was important that we provided a common HPC resource so that the participants could upload their solution data, run an automated post-processing workflow, and produce standardized outputs. Many cases were processed from many different groups with different grids, different solvers, but that enabled side-by-side comparison. We also delivered the higher order features like the vortex path. This was done automatically, also for comparison. And in the end, we were able to share images, but also data in the portable XDB format so that people could extract knowledge and further their understanding. And all of this was required, in order to do this, really a partnership was required between all of the CFD users, all the practitioners, and Intelligent Light and our systems. And this is an example of work that we do to customize and automated workflows. And we'll be happy to discuss with you, all the people who came today to participate in this webinar on how we might customize a workflow for you. So again, I'd like to thank the three presenters, Michael, Earl, and Nathan. And I'd like to thank you for joining us today. We're going to move on to our Q&A. And as I said before, we can you can use the chat feature in the lower left corner of the ReadyTalk window, and then I will read those questions and allow our presenters to ask. We have one here for Earl, which is about the, let me see, Earl. It says, for the secondary vortex structures, are the axis of rotation perpendicular to the primary vortex axis, i.e., are they induced?
Yeah, some of them were and some of them aren't. It's really interesting. Some of the vortex structures, when they break up, you'll start to see them creeping upward, and they are perpendicular to the primary vortex, whereas others, they'll break up and they're not. So there's kind of a mixture of both. Some of the results, some of the contributions had more of that than others.
So let me comment on that. This is Nathan. Primarily, this is when you have vortex braids in a helical pattern in close proximity, they do tend to have mutual inductance. What's happening here is it is probably happening, we are capturing more of it than what is physical, because most of the hover, experimentally observed hover, tends to show that it's fairly stable, the system is fairly stable, but our real high fidelity simulations tend to break it down. There's a lot of effort going on right now around different groups to figure out what's the source of it. Interestingly enough, in several instances, the net vorticity, vertical content in the flow field doesn't change, so therefore the loads are, the aerodynamic loads are pretty accurate. It's unsteadiness that small scale unsteadiness induces. But answer the question in short, for most parts it is. It is mutual inductance instability. If you take a very close look at it, it does show the chaining, 3D chaining effect between the successive grades.
Okay, thank you, Nathan. Here's another question. Is it possible to do to be able to difference pairs of the solutions or compute a mean or RMS of multiple solutions? Earl, do you want to take that one?
Yeah, that can be done within the XDB workflow. So one thing one would do is create different slices, and then on those slices, you can map all the different solutions to that same slice, and then do differences and do means and additions, things like that. That's very, very doable. I've actually done that with different projects.
Well, actually, that leads into a different question we had, which is, it was for Nathan actually, which is, as this workshop continues, the understanding is that this workshop is an ongoing effort. Do you imagine that you would, what might you add or expand to the automated workflow on the post-processing side?
On the post-processing side, so that's an interesting question. Our initial model was to, the tough part was to get all the different formats into a standardized script, earlier the heavy lifting there. And so the initial model was to get the data hosted into a centralized place, and that makes it with the scripts vetted out so that everything is consistent. Going forward, we might even consider the model of taking all the scripts and getting the participants to do it themselves. But we are just scratching the surface here to some extent. There's so much data here, so much mining to be done. It's a question of digging further in. For example, there's the problems like state breakdown. There's so much physics to be gotten out of it to try to figure out exactly where things are going in terms of where does the breakdown initiate, what are the triggers, what conditions does it do, and every simulation is different. So what I envisage, it's because of the size of the simulations, sometimes it's a slower process than the smaller simulations, and we have an yearly cycle to go with this. What I would envisage is more of this, perhaps distribute the scripts out to the participants directly, and not necessarily having all of them upload the data. So that would give them time to do it at their own pace. But I think this is just the start in terms of having these 3D data sets. And so far we have only dealt with a single point data. We haven't really gone on to see truly unsteady data sets and try to figure out what is there. But that's a much more difficult proposition. So there's a lot more runway to go with this.
Lots of different possibilities. And going back to the previous question about wanting to do comparisons of solutions, that's something that we would take in from the practitioners, like you said, Nathan. We ask what the people who are doing the project want to see, and we can change the workflow, add additional things to the workflow as needed. All right, so another question. What did the participants really have to do? Did they just upload their data? How did they run the script? How did they do the downloads? What happened there?
Right. So this is Earl. So the user, the participants, they had to upload their data. The data had to be meet some. There were some specs, like they had to identify the rotor blade, the boundary through a boundary surface. So, and that was it. Once they uploaded it, we brought it across from the anonymous FTP site onto the main cluster systems at our systems, and then fired off the scripts, and then the scripts created the XDBs, and we brought the images, the XDBs down to create the images. That was it.
Okay. Once again, going back to the previous question about comparison, because we were providing the XDBs to all the participants, if they had FieldView, they could do their own comparison, because comparison is something that's built into FieldView.
Right, and with the current version of FieldView, they can also, they can load in the different XDBs and do differences between them, and so if you wanted to make a difference between them, you can do that. Also addressing one of that earlier question on essentially they're wanting to do differences and do other things like compute needs and RMS of multiple solutions. I'm actually doing that with other projects within an XDB workflow where I'm doing uncertainty quantification. So I have 4 different grid resolutions, and I need to get a Richardson extrapolation. I'm doing that within FieldView. So that those are lots of methodologies that you can apply to these extracts.
Lots of possibilities depending on the needs of the users, right?
Yeah, definitely.
All right, here's another question. On average, how many cores were needed to produce these solutions, and how long would the individual jobs run in clock time?
Let me take that. I assume they're asking about the solution themselves, not just the processing aspect of it. So that really depends. We had codes running Helios or Overflow with close to 500 million points, but a lot of them are Cartesian points, and that would take maybe a week for a complete converged solution. Then there are other codes which probably run with 50 million points, completely unstructured, perhaps a couple of days. But I haven't seen any reasonable house solutions running within a day based on complete capturing of the wake. There are methods where there are vortex-based methods, filament methods, which can do faster than that, but they have their own set of issues when compared to first principles methods. So short answer is it depends on how much grid points you put in there and how much you refine the wake. But the most adapted solutions I have seen for US60 and the TRAM type of calculations, it's probably anywhere from 4 to 5 days to a week on, say, 1,200 codes or thereabouts.
Yeah, this is Earl. Also on the post-processing side, these were all ran using parallel FieldView. So for these cases, we were using 16 cores on one compute node, and that was over at our systems, and they had plenty of memory on each one of those nodes in order to handle that. So with this, we're handling everything from 500 million grid points down to, not that much, but maybe a couple 100,000 grid points. So we were, within this post-processing, we were handling things that were small to extremely large with some of them had thousands of grids, particularly the adaptive cases that we ran. So that was on the post-processing side.
Thank you. Okay, another question is, could you explain a little bit about the difference between an XDB workflow and using remote graphics on
Right. Yeah. So
system?
with this XDB workflow, we created the extracts all in batch. So the FieldView resided on the remote systems at our systems, and then we created FVX, FieldView FVX programs were created, and we ran FVX on the queuing system on those remote systems. So within that, we would the output from that job would be FieldView XDBs. Remote graphics means I'm sitting here on my laptop, and then using client server, I'm connecting to the back-end systems, loading the volume data or the XDBs client server with the server running on the remote system at our systems, and I'm able to interactively explore the data set connected to the bigger systems on the back end.
Right. And as you mentioned earlier, that was part of the setup, right?
Yeah. So one of the issues there when we first were doing this, I was looking at the cases that I ran, and that had 500,000 grid 500,000 grid points and 2,000 grids. And there's no way I was going to load that on my laptop, so I was able to keep that on our systems, load that in parallel, and then interactively explore that data set from my laptop.
And there you did the setup for some of the automated workflow.
Yeah.
And then,
So
and then the automated workflow exports the XDBs, and then many of the comparisons or the pictures were used with XDBs as the data set. And then
and also I would then save a restart, and from that restart would be a FVX file. And then I can take that FVX file as the beginning of my scripting of all the other types of data sets. So for instance, I was loading a Overflow 2 data set, and I can change that to other types of data sets within that script, and we were able to easily replicate that for all different types of grid types.
Right. So then when you do the automated post-processing runs with the XDBs, you also get the XDBs, which, as you mentioned, are 10 to 100 times, maybe more.
100 to 1,000 times. Yeah,
hundreds to thousands times smaller. And then that makes it easy to get the data down off of the remote HPC resource, and it's small enough to interact with on your desktop.
Exactly.
So, okay. Let's see. Are there any more questions? We will be on the line for a few more minutes, so if you do have more questions, please use the chat feature and chat in. Did I miss any?
Shane, I see one. Can where do I get the call for 2018 workshop?
Yes, sure. Yeah, can I get these slides for the 2018 workshop? I guess we'll have to deal with that one offline, but you know that person? Nothing?
No, I don't think I have that contact. So if they can shoot me an email, I can send them the info.
Sure, I can facilitate getting you that email so that that person can get invited to next year's workshop. That'd be great. All right, so I haven't seen any new questions coming in a little bit. Again, I did want to thank everybody for joining the webinar and spending your time with us. Thanks again to Nathan and Michael and Earl. But we will stay on the line for a little bit longer in case more questions come up. If not, thank you very much and hope to see you again at another Intelligent Light webinar.
All right, thank you.
you're open.
Okay, we do have one more question here. And the question is about the scripts, the automated post-processing. Was this one script or a set of scripts that could be applied to all data sets? How did that work?
Right. So we had different scripts for different features. So we had scripts for creating the isosurfaces and different scripts for creating the particle or the vortex tracker. And yeah, once we had created the scripts for overflow, for instance, that was applicable to data sets that were FVU and S. So yeah, they were usable for, once it was created and verified for one data set type, we were able to utilize those scripts for other data set types.
Gotcha.
And for many of those, it was simply changing the reader. So one would be, for instance, overflow reader, another one would be plot3d reader, the other would be FUNS reader, and it worked. It went right across.
Okay.
Yeah.
Thank you.
This is Michael. I have something to add to the previous question of XPD over remote graphics. So when you're using the XPD, you get a lot better latency and performance when you're viewing and modifying your model. To do high-performance remote visualization, you generally need to submit to a 3D accelerated viz queue, which increases costs and still increases the latency from your interactive session.
So efficiency from the interactive point of view.
Yeah, efficiency and responsiveness for the interactive point of view, and it also costs less because you don't have to reserve a 3D capable node to then launch another third-party solution to do remote 3D visualization.
Right, and also, but with one of the things too within FieldView is that we do client server, and that's another way we can do our graphics.
Thank you, Michael. Okay, and as I don't see any more questions coming in, we will end the session. And again, thanks everybody for participating. Thanks, Michael. Thanks, Nathan. And we'll see you again in the future.
All right, thank you.
Thank you.